everybody, welcome back. Today we're going to be talking about the physiology of equilibrium. And in order to do that, we have to talk about the inner ear. So remember, the inner ear is a shared space where hearing and equilibrium receptors are housed. These receptors are going to send information to the brain on cranial nerve number 8, the vestibulocochlear nerve. The hearing receptors we've already learned about are housed in the cochlea, which is shown here in yellow. The receptors for equilibrium are in the vestibule and the semicircular canals, shown in green and blue here. They're in two places because we monitor two different types of equilibrium, static and dynamic. Static equilibrium tells us the position of our head relative to gravity. This is determined in the area of the inner ear called the vestibule, shown in green here. Dynamic equilibrium is when we're able to detect movement in three-dimensional space, including rotation. The receptors for dynamic equilibrium are in the semicircular canals, which are shown here in blue. These receptors work the same way as hearing receptors. Fluid movement causes a mechanical change in the receptor, and transduction converts the energy of the movement into an electrical signal, which initiates an action potential along the neuron. These vestibular receptors send information to the vestibular nuclei in the pons and the medulla, where this information, as well as input from somatic proprioceptors from the muscles and tendons and joint capsules, as well as visual information from the photoreceptors in the eyes, is all integrated together. Let's talk first about static equilibrium. Static equilibrium is used to determine the position of the head relative to gravity. For example, if I was to put a bag over your head and put you in the trunk of my car, and then I parked that car on an incline, you would know that you are not on a level surface. The receptors that send this information to the brain are found in the walls of two chambers of the vestibule, the utricle and the saccule. The utricle lies horizontally. The saccule lies vertically. The maculae are the sensory organs of static equilibrium, just like the organ of Corti is the organ of hearing. You have two maculae on each side of your head. One is in the utricle and one is in the saccule. The one you're looking at is the macule of the utricle. You can see that it is laying horizontally. It consists of a gelatinous membrane which is filled with tiny little stones made of calcium carbonate. These are called otoliths. We also have supporting cells as well as our hair cells, which are our receptors. When the head, and therefore the utricle, is completely level, the otolithic membrane rests right on top of the utricle. The gravitational force is directly down and doesn't pull on the otolithic membrane in any particular direction. The hair cells, you can see, are sticking straight up into the gel-like membrane. However, if the utricle is on an incline, gravity pulls on the otoliths, causing the otolithic membrane to sag downwards towards gravity. This movement bends the hair cell receptors, causing transduction of the mechanical force into an action potential in the first-order neuron. The same physiology applies to the maculae of the saccule, except it is normally in a vertical position, and the receptors are activated when it becomes more horizontal. Static equilibrium not only helps you tell if your head is tilted to one side or the other, or if you are leaning forward or backwards in space, it also helps you detect what we call linear acceleration, as in when you are in a car that is speeding up, you can feel that you're going faster, or vertical acceleration, which is like when you're in an elevator and it starts falling. Dynamic equilibrium is the detection of movement through three-dimensional space. The receptors are in the semicircular canals, shown here in blue. Remember the example I gave you of you being in the trunk of my car. You can tell using static equilibrium whether you're parked on an incline or whether we're accelerating. With dynamic equilibrium, we can tell when we go around a corner, as well as whether the driver turned left or right to do it. The receptors that send this information to the brain are found in each of the three semicircular canals. However, this is still working on the same principle that transduction occurs when the fluid in the semicircular canals pushes against a mechanoreceptor, causing transduction. The cristae are the receptors of dynamic equilibrium, just like the organ of Corti was the receptor organ of hearing, and the maculae are the receptors for static equilibrium. Each semicircular canal has an enlarged area called an ampulla near its base where it joins with the vestibule. The ampulla is filled with a fluid called endolymph, and it also contains a gelatinous membrane called the cupula that has hair cells that stick up into it. When the head rotates along one of the axes of the semicircular canals, the fluid in that canal that is parallel to that axis will lag slightly behind and will pull on the cupula, bending it a bit. This movement bends the hair cell receptors, causing transduction of the mechanical force into an action potential of the first order neuron. You can tell which way you are rotating because the fluid on one side of the head will move in one direction, depolarizing the neurons, while on the other side, the neurons become hyperpolarized because the cupula gets bent in the opposite direction. Sometimes movement is in just one of the canals, and sometimes movement happens in more than one of the canals. Integration of input from all 6 cristae helps your brain determine that you are indeed turning and in which 3-dimensional direction. Let's talk about an example. If you were to suddenly turn your head to the right, the bones of the semicircular canals will move quickly because they're attached to your head. But the law of inertia says that the fluid will lag behind slightly. The fluid will drag on the cupula in the right ear, bending it medially. This depolarizes the first order neurons and sends an action potential. However, in the left ear, the movement of the head suddenly to the right will cause the bones to move to the right, and the fluid will lag behind, but the cupula will now be pulled laterally. This causes hyperpolarization of those first order neurons, no action potential. By integrating responses from both ears, your brain knows that you have turned to the right. The reason you get dizzy after you've been spinning around and around is that the fluid finally catches up with your movement, and the stopping of movement is going to cause the fluid to slosh back in the other direction. Now the receptors will hyperpolarize on the right and depolarize on the left, making your brain feel like it has lost its grip on equilibrium for a moment. The vestibular pathway shows us that axons from both the vestibule and the semicircular ducts merge to form the vestibular branch of cranial nerve number 8. The information heads to the pons and the medulla, where integration with other signals occurs in the vestibular nuclei. As with most other sensory information, this input is routed through the thalamus to the cerebral cortex, where you will become aware of the position and movement of your body in space. Input is also sent to the vestibulospinal tract, which maintains body position and tone, as well as input to other cranial nerves to maintain focus and enable visual tracking. There are a few things that can cause vision disorders. Cataracts results from cloudiness of the lens. This usually happens later in life and is due to changes in the proteins that make up the lens. Glaucoma is caused by high intraocular pressure due to too much aqueous humor at the front of the eye. Macular degeneration is when you have a death of the photoreceptors, so that even though light is hitting the back of the retina, no transduction is happening. We also have a few hearing disorders to discuss. Meniere's disease is when there is too much endolymph in the cochlear duct. This pressure could either inhibit or stimulate hair cell activation. A characteristic of Meniere's disease is tinnitus from inappropriate hair cell activation. Presbycusis is normal age-related hearing loss. This is often due to the breaking of the hair cells in the cochlear duct due to accumulation of damage throughout the lifespan. Hair cells are not able to regenerate in humans. Deafness can be caused by many different things. Damage to the receptors, damage to the cranial nerve, damage to the auditory ossicles. A cochlear implant is a transmitter receiver that converts sounds into electrical signals that are transmitted to the cochlear neurons. These can be used to bypass issues with hair cell damage or auditory ossicle damage. That's it for today. See you in class.